Okay, so this is probably your first sort of grown-up theorem in this class. So I want to prove the following theorem, which consists of two if and only if statements. If statement number one, so if you have a sequence Sn, statement number one is that if a limit of a sequence Sn is defined, if it exists, then lim_inf of the same sequence is equal to lim_sup of the same sequence, and both are equal to the limit of a sequence itself. Notice that this is valid for both infinity, minus infinity, and a finite value of a limit. In what follows, I'm going to prove only the case when the limit is finite, and you should look in the book for an alternative when the limit is infinite. So it will be your responsibility to take a look at the statement about infinite limits in this context. All right, so and the opposite statement is also true, that if lim_sup and the lim_inf of a given sequence are the same, then the limit exists, and the limit is equal to both lim_sup and lim_inf. Again, this is valid both for infinite and finite limits, and we're only going to look at the case of a finite limit. Now, just to motivate again why this would be true, remember that the meaning of lim_sup and lim_inf is the following, that both are going to give you the window within which your sequence is going to be oscillating as the sequence goes, as n goes to infinity. So then if the window is going to collapse into one point, if the upper limit of the window and the lower limit of the window are exactly the same, then that means that your sequence is going to be squeezed between these two limits and between these two boundaries of the window. And so if both boundaries coincide, if you're oscillating between the same number, then the limit must exist and be equal to that number. And so this should be true if if the window is going to reduce to a single point window of oscillations will only reduce to a single point at infinity when n goes to infinity, then you expect that the limit exists. And if the limit exists, then vice versa, you would expect that there is no room for oscillations, because if there was a room for oscillations, then the limit could not exist. So let's prove item number one first. So item number one, you're assuming that your sequence converges to some number, let's call it S. And if it does converge, then of course the definition of a limit is going to hold. For any epsilon greater than 0, there should exist a capital N and R, such that if index exceeds this capital N, then Sn minus S is less than epsilon, right? That's about 1,000th time when I repeat the definition of a limit here. All right, so then I'm going to try to rewrite the same expression without using absolute value sign. So this means that Sn minus S is less than epsilon and bigger than minus epsilon if n is bigger than capital N. Or if I add S to three signs of inequality, S minus epsilon is less than Sn, less than S plus epsilon, once again, if n is bigger than capital N. All right, so then if I choose any k, which is greater than n, then if k is bigger than n, then for n greater or equal than k, all Sn should be less than S plus epsilon. And all Sn should be bigger than S minus epsilon. And so if I then take a tail of my sequence starting from k, then it would follow that s plus epsilon is an upper bound on the tail, and s minus epsilon is a lower bound on the same tail. Right? Again, if I choose k greater than n and n greater than k, then n is bigger than capital N, so this should hold. So if n is greater or equal than capital K, than k, and I take a supremum, the supremum must be less or equal than s plus epsilon, because s plus epsilon is an upper bound on the tail of a sequence, and the supremum is the least upper bound. And likewise, s minus epsilon is a lower bound on the tail of my sequence starting from k, and infimum is the greatest lower bound. So that means that the supremum must be less or equal than s plus epsilon, infimum must be greater or equal than s minus epsilon. Right? So if k is greater than n, then both of these statements should be true. Okay, but now what do I have then? I have a sequence. Remember, this guy I called vk, this guy I called uk. So for all k bigger than capital N, vk is less or equal than s plus epsilon. S plus epsilon by itself can be thought of as a constant sequence. So then I have a sequence vk, which is less or equal than a constant sequence. So the limit of vk must be less or equal than the limit of a constant sequence, and the limit of a constant sequence is precisely that constant at the limit of which you're taking. So if I take a limit of this side of an inequality, it should be less or equal than the limit of this side of inequality by a theorem that we proved in the last installment of this lecture. So from this inequality, by taking limits of both sides, I arrive at this. And by taking limits of both sides here, I arrive at that. But then what is limit as k goes to infinity of a infimum as n is greater or equal than k? That's a definition of lim inf. And this is a definition of lim sup. So lim sup then is less or equal than s plus epsilon, right? That's from here. And lim inf is greater or equal than s minus epsilon. But also by a theorem from the last lecture, we also know that lim inf is always less or equal than lim sup. And so what we discovered is this, that for any epsilon that is as small as you wish, this chain of inequalities is true. Well, but then if this is true for any epsilon, then I can take epsilon in here to be as small as I wish, or I can let epsilon go to 0. If I let epsilon go to 0, then epsilon is gone, and I just have that left. But then everything here is squeezed between s. S is greater or equal than lim inf at lim sup, and both are greater or equal than s. So that means that, in fact, everybody is equal to s. Right? Lim inf and lim sup are both less or equal than s and greater or equal than s. They must be equal to s. And that is exactly what I set out to show. Okay, so now we are proving the opposite statement. So in the first statement, we assume that the limit of Sn exists, and then we show that lim sup is equal to lim n. Now we're doing the opposite. So I'm going to assume that lim sup and lim n are both equal to s. By the way, we showed last time that lim sup and lim n, unlike limit, those two always exist. No matter which sequence you take, you should always be able to find lim sup, and you should always be able to find lim n. So let's say both are equal to s. So my window of oscillations at infinity reduces to just 1 point. And so I want to prove my conjecture that in this case, actually the limit of Sn should be equal to the same S. All right, so if I want to get to the limit, I need to end up with a definition of a limit. Any good definition of a limit starts from us choosing epsilon greater than 0, so let's do that. And then I should be able to find capital N, for which if n is bigger than capital N, then Sn minus S is less than my epsilon. Okay, that's what I need. Here is what I have. I know that lim_inf of Sn is equal to S. And that means that the limit as k goes to infinity of these UKs, right? UKs were in thema of Sn when n is greater or equal than k. Limit of UK is equal to S. And because it's equal to S, by definition of a limit UK, there should exist some number capital K1, such that if k is bigger than K1, then UK minus S is less than epsilon, right? That's a definition of a limit. Limit of UK is S. In a similar vein, because lim_sup of Sn is equal to S, what was lim_sup of Sn? Lim_sup of Sn was the limit as k goes to infinity of suprema of Sn when n is greater or equal than k. And those suprema I denoted by Vk. So because I know that the limit of Vk is S, then there exists another number, K2, capital K2, such that if k is bigger than K2, then Vk minus S is less than epsilon. Right, so I'm getting this from the fact that lim_sup and lim_inf are limits of UK and Vk. Okay, so in this case, then let's do the following manipulation. Let's make little k a maximum of this big capital K1 and K2 plus 1. Okay, so then if little k is like that, if it is by 1 larger than the maximum of K1 and K2, then k must be bigger than K1. And if k is bigger than K1, then from here, I know that if k is bigger than K1, I know that UK minus S is going to be less than epsilon. And for a similar reason, k also is bigger than K2 because it's larger than the maximum of K1 plus K2. Maximum of K1, K2 plus 1. So this is bigger than K2. And therefore we have also that Vk minus S is less than epsilon. All right, so how do we use this? I'm going to rewrite both expressions without using absolute value sign. So that's what we're going to get. Okay, and then I'm going to use halves of each inequality. So from a fact that UK minus S is bigger than epsilon, if I add S to both sides, then S minus epsilon is less than UK. And who was UK? UK was in themum of Sn when n is greater or equal than k. Right, that was the definition of UK. Likewise, from here, if I use the second part of the inequality, Vk minus S is less than epsilon. That means that Vk is less than S plus epsilon. But Vk itself is a supremum of Sn when n is greater or equal than k. What this gives me is the following. So this says that the supremum when n is greater or equal than k of Sn is less than S plus epsilon. What is a supremum? Supremum is the least upper bound. So the least upper bound is less than epsilon. Least upper bound over Sn when n is greater or equal than k, of course. But if the least upper bound is less than S plus epsilon, then S plus epsilon itself is an upper bound on Sn starting from k. So that means that Sn must be less than epsilon s plus epsilon whenever n is greater or equal than k. Similar thing for the infimum. uk is less than s minus epsilon. uk is the infimum of Sn starting from k. So this is the greatest lower bound of Sn when n is greater or equal than k. And this greatest lower bound is bigger than s minus epsilon, so that means that s minus epsilon in turn must be a lower bound on Sn when n is greater or equal than k. So we have this inequality. And now, as a last step, I'm going to set capital N to be exactly k, and I'm going to take n bigger than n, than this capital N. But n bigger than capital N also means that n is bigger than k. N bigger than k implies that Sn is less than plus epsilon, and from here it also implies that Sn is bigger than s minus epsilon. So if n is greater than n, then these chain of inequalities holds. But saying s minus epsilon less than Sn less than s plus epsilon is the same thing as saying this if I subtract s from all three sides. And this is an alternative way of writing that Sn minus s absolute value is less than epsilon. Okay, so given epsilon some 10 minutes ago, over here, I was able to go through all these calculations, and at the end of the day, I found capital N such that if n is bigger than capital N, then Sn minus s is less than epsilon. What does that mean? That means precisely let the limit as n goes to infinity of Sn exists, n is equal to s.